The infrared sensor array on Mauna Loa recorded something unusual just before dawn, a streak of light moving through the star field at 17 kilometers per second, faster than anything bound to the sun should travel. At first, the automated system flagged it as noise, a pixel error in the vast digital canvas of Hawaiian sky. But the pattern returned across 4 successive nights, each time tracing the same hyperbolic path through Orion's shoulder. Astronomers reviewing the data noticed what the algorithm had missed. This object carried no orbital signature matching any known comet, asteroid, or debris from the outer solar system. The velocity excess suggested it had crossed interstellar space, arriving from somewhere beyond Neptune's cold frontier. As it approached perihelion, its closest pass to the Sun, spectroscopic analysis revealed carbon-rich, water-poor chemistry similar to ʻOumuamua's strange profile. Then, without warning, without jets, without any precursor event, the object came apart. What kind of visitor survives 4 light-years of frozen void, only to disintegrate in silence where heat should have protected it? The Atlas telescope network maintains constant surveillance across both hemispheres, scanning 40,000 square degrees of sky every 2 nights. The twin facilities, one perched on Haleakala in Maui, the other on the volcanic slopes of Mauna Loa, function as humanity's early warning system for near-Earth objects. Their cameras capture everything from tumbling space debris to main-belt asteroids drifting through predictable orbits. Most nights pass in algorithmic silence. Data streams through fiber optic cables to processing centers where machine learning filters separate cosmic wheat from digital chaff. On October 3rd, frame number 7841 from the Mauna Loa array contained an anomaly. The detection occurred at 0447 Universal Time, when most of Hawaii still slept beneath star-filled darkness. A faint point source appeared in the constellation Gemini, magnitude 19.4, barely visible above the noise floor. The automated pipeline measured its motion, 2 arc-seconds per minute, consistent with a solar system body in the inner regions. But something in the velocity profile triggered a secondary flag. The object moved too fast for its apparent distance. Within 6 hours, confirmation images arrived from the Panoramic Survey Telescope and Rapid Response System located on Haleakala. The cross-validation removed any doubt. This was real, not an artifact of sensor defect or satellite glint. Astrometric measurements refined the trajectory. The numbers revealed a story written in gravitational mathematics. This visitor carried excess velocity beyond solar escape threshold, indicating an origin outside the gravitational dominion of the Sun. The Minor Planet Center in Cambridge, Massachusetts, received the preliminary orbit computation by noon Eastern Time. Staff astronomers ran the data through orbital, dynamic software designed to distinguish bound objects from interstellar interlopers. The solution emerged with statistical confidence exceeding 5 sigma, hyperbolic excess velocity measured at 3.1 kilometers per second. In the sparse catalogue of confirmed interstellar objects, containing only ʻOumuamua discovered in 2017 and comet Borisov identified in 2019, this would become the 3rd known visitor from beyond the solar neighbourhood. The designation followed standard protocol. Interstellar objects received the prefix I for interstellar, followed by the year and discovery order. Internal communications tagged it provisionally as 3I, awaiting formal confirmation. But the astronomical community knew it more familiarly by its Discovery Survey name, 3I Atlas. Unlike its predecessors, this object arrived on a trajectory that would graze perilously close to the Sun, a sun-grazer path reminiscent of the Kreutz family comets that periodically dive into the solar corona. Spectroscopic observations began immediately. Telescopes in Chile, Hawaii, and Spain pointed their instruments toward the incoming visitor. The light reflected from its surface carried chemical fingerprints, absorption lines revealing molecular composition. Early spectra showed strong carbon absorption bands with minimal water signatures. The surface appeared dry, carbon-rich, possibly similar to the organic heavy asteroids found in the outer main belt. But those local bodies formed in the Sun's protoplanetary disk. This object had condensed around another star, in a molecular cloud with different chemistry, perhaps different ratios of carbon to oxygen, different temperatures in the planet-forming zone. As October progressed, 3I Atlas brightened slightly, its approach bringing it closer to Earth's orbit before swinging sunward. observatories tracked its rotation, searching for periodic variations in reflected light that might reveal shape or surface features. The light curve remained remarkably stable. No significant fluctuations, no signs of tumbling or complex spin. This stability suggested either a nearly spherical form or a rotation axis aligned with Earth's line of sight. The NASA Jet Propulsion Laboratory in Pasadena refined the trajectory daily as new observations accumulated. The orbital path became increasingly certain. Perihelion, the point of closest solar approach, would occur on November 19th at a distance of just 0.27 astronomical units from the Sun's photosphere. This placed it deep within the orbit of Mercury, inside the zone where solar radiation becomes intense enough to vaporize ice and crack stone through thermal stress. For typical comets approaching the Sun, this region triggers dramatic transformation. Solar heating penetrates the surface layers, warming volatile ices trapped within. Water, carbon dioxide, and methane sublimate directly from solid to gas, building pressure beneath the crust. Eventually the surface ruptures, jets of gas and dust erupting into space, forming the characteristic coma and tail. These outgassing events follow predictable patterns, well documented across thousands of cometary observations, but 3 Atlas displayed none of these expected behaviours. As it crossed inside Mars's orbit in early November, instruments detected no gas emissions, no expanding coma, no dust production above background levels. The object remained point-like in even the most sensitive images, its appearance unchanged from discovery. This silence troubled researchers familiar with cometary physics. An icy body at this solar distance should respond to heating. The lack of activity suggested either an object depleted of volatiles, a dead comet stripped of ice during previous solar passages, or something compositionally different from familiar solar system comets. Theoretical models attempted to explain the discrepancy. Perhaps the surface had developed a thick, insulating crust of refractory material, sealing volatiles beneath an impermeable layer. Or perhaps interstellar radiation had processed the surface during its long journey, creating a carbon-rich mantle resistant to solar heating. Some researchers noted the similarity to ʻOumuamua, which also exhibited no cometary activity despite passing well within the zone where ice should vaporize. The infrared observatories contributed additional data. Spitzer Space Telescope observations before its retirement had provided thermal measurements of ʻOumuamua, revealing an elongated, tumbling object with unusual reflectivity. Similar thermal observations of 3 Atlas proved more difficult. The object was fainter, more distant during optimal viewing windows. Still, infrared measurements suggested a small body, perhaps 50 to 100 meters in diameter, with moderate thermal inertia consistent with rocky or carbonaceous composition. As mid-November approached, the astronomical community prepared for perihelion passage. This would be the critical test. If 3 Atlas contained any volatile materials, the intense solar heating near closest approach would force their release. Temperatures on the sunward side would exceed 600 degrees Celsius, hot enough to melt lead, hot enough to break chemical bonds in complex organic molecules. Ground-based telescopes coordinated observation campaigns. Solar observatories prepared to track the object through coronagraphs, designed to block the sun's overwhelming glare. The Solar and Heliospheric Observatory, stationed at the L1 Lagrange point, aimed its white light coronagraph at the predicted path. The stereo spacecraft, viewing the sun from different angles, would provide stereoscopic coverage. Even amateur astronomers with specialized solar filters anticipated glimpsing the visitor's final approach. The days before perihelion passed in mounting tension. Would 3I Atlas survive intact, proving itself a solid body resistant to thermal disruption, or would it fragment like so many sun grazers before it, torn apart by thermal stress and tidal forces? The historical record of sun-grazing comets offered little comfort. Most never emerged from perihelion, their material dispersing into the solar corona, leaving only fading dust streams as evidence of their existence. November 18th arrived. Final observations before solar conjunction captured 3 Atlas still intact, still silent, showing no signs of distress. The surface temperature models predicted the object would reach peak heating within hours of perihelion, then begin cooling as it receded. If volatiles existed beneath the surface, they would mobilize now or never. Researchers reviewed the data accumulated over 6 weeks of tracking. Every measurement, every spectrum, every astrometric position fit within expected parameters for a small, inactive body on a hyperbolic trajectory. Nothing suggested the coming event. No precursor activity, no jets, no fragmentation halo. The object appeared stable, inert, prepared to endure solar passage as it had presumably endured the cold of interstellar space for millennia. But appearances deceive. The data revealed only surfaces, only reflected light, only what instruments could measure from millions of kilometers away. The interior remained unknown, its structure, its composition, its hidden weaknesses. Whatever processes had formed this object in another stellar system, whatever chemistry governed its cohesion, whatever history it carried across the galaxy, all these factors remained invisible, locked within the visitor's core. If it carried ice, why showed it no warming signature? And if it didn't, what held it together through temperature extremes spanning hundreds of degrees? What breaks in silence, without pressure, where heat should protect structure? The coronagraph images from the Solar and Heliospheric Observatory began arriving at 0230 Universal Time on November 19th. Automated processing cleaned the frames, removing cosmic rays and electronic noise, leaving only the faint stars and any transient objects crossing the instrument's field of view. The Sun itself appeared as a black occulting disk, its blinding light blocked by the coronagraph's optical system, revealing the pearly corona streaming outward in complex magnetic structures. 3i Atlas entered the field at 0315, a faint point of light moving against the background stars. Its position matched predictions within arc-second precision, orbital mechanics working as expected, gravity pulling the visitor along its calculated path. The object's brightness increased gradually as it approached perihelion, sunlight reflecting from its surface growing more intense with decreasing distance. Ground controllers at NASA's Goddard Space Flight Center monitored the telemetry. The chronograph operated in automatic mode, capturing images every 12 minutes, building a time-lapse sequence of the perihelion passage. Similar observations were underway from the twin stereo spacecraft, positioned 90 degrees ahead and behind Earth in its orbit, providing three-dimensional coverage of the inner heliosphere. Perihelion occurred at 0447 Universal Time. At that moment, 3i Atlas passed just 40 million kilometers from the solar photosphere, deep within the Sun's outer atmosphere. Solar wind, a supersonic stream of charged particles, screamed past at 400 kilometers per second. The temperature in the corona reached 1 million degrees Celsius, though the tenuous density meant actual heating depended on radiative transfer from the visible photosphere below. The light curve from SOHO showed expected brightening as the object reached its closest point. Peak magnitude occurred within minutes of perihelion, then began declining as 3i Atlas started its outbound journey. For several frames, everything appeared nominal. The visitor had survived initial heating, maintained structural integrity, showed no signs of catastrophic disruption. Then frame 0143, captured at 0511, revealed a change. The point source had developed a slight elongation, a subtle blur in the direction perpendicular to its motion. Image analysis initially flagged it as potential motion smear, a timing error in the exposure. But the next frame confirmed the elongation had increased. By 0535, the object clearly showed a dispersing cloud, brightness distributed across several pixels rather than concentrated in a single point source. The fragmentation event had begun. Somewhere between frame 0141 and 0143, a span of 12 minutes, 3i Atlas had started coming apart. The process accelerated over the following hour. Subsequent images showed the dust cloud expanding, brightness falling as material spread across a larger volume. By 0700, the original object had vanished, replaced by a diffuse plume stretching across thousands of kilometers. Multi-instrument confirmation arrived from stereo and ground-based solar telescopes. All observers recorded the same sequence: stable approach, perihelion passage, then rapid disintegration shortly after closest solar approach. The timing proved critical. The breakup occurred not during maximum heating at perihelion, but 24 minutes afterward, when the object had already begun receding and cooling. This delayed failure pattern suggested something other than simple thermal stress. Researchers at the Harvard-Smithsonian Center for Astrophysics retrieved archival data on previous sun grazer fragmentations. The Kreutz family, a population of comets originating from a single massive progenitor that broke apart centuries ago, provided hundreds of comparison cases. These comets typically disintegrated during perihelion passage, torn apart by tidal forces or thermal stress at closest approach. Their light curves showed characteristic patterns, brightening to peak, sudden enhancement as internal, volatiles erupted, then rapid fading as the cloud dispersed. The 3I Atlas fragmentation displayed different characteristics. The light curve spike came after perihelion, not during. The brightness enhancement appeared more gradual, lacking the explosive signature of catastrophic outgassing. Analysis of the dust cloud's expansion velocity showed material moving at roughly 200 meters per second, fast by human standards, but slower than typical cometary jets produced by explosive sublimation. Spectroscopic observations captured during the breakup revealed another anomaly. The ejected material showed strong carbon signatures consistent with the pre-fragmentation spectra, but water bands remained notably absent. If ice sublimation had triggered the breakup, the expanding cloud should contain substantial water vapor. Instead, the spectrum suggested dry dust, carbon compounds, possibly complex organic molecules, but little to no water. The fragmentation produced dust, not gas, an unusual profile for a body breaking apart near the Sun. Orbital dynamics specialists at the Jet Propulsion Laboratory modelled the post-fragmentation trajectories. The dust particles, no longer bound by the object's self-gravity, followed independent orbits determined by their ejection velocity and solar radiation pressure. Larger particles stayed closer to the original trajectory, while smaller grains, more strongly affected by radiation pressure, were pushed outward, forming an elongated tail. Within days, the debris cloud stretched across millions of kilometers, individual particles dispersing along the orbital path. Attempts to detect large fragments proved unsuccessful. If the object had split into several sizable pieces, they should remain visible in follow-up observations. But deep imaging from observatories in Chile and Hawaii found no discrete remnants above the detection threshold. The fragmentation appeared complete, a total structural failure that reduced the entire visitor to rubble and dust. The mechanics of this failure puzzled researchers familiar with small-body physics. Comets typically break apart through three primary mechanisms: tidal disruption, when gravitational gradients exceed internal cohesion; rotational disruption, when spin rates generate centrifugal forces that overcome strength; or thermal disruption, when heating creates internal pressure that fractures the structure. Each mechanism produces characteristic signatures in the observational data. Tidal disruption seemed unlikely. The gravitational gradient at 3I Atlas's perihelion distance was insufficient to tear apart even a loosely bound rubble pile. Calculations showed the tidal stress reached only a small fraction of typical cometary strength. Objects had survived far closer solar approaches without tidal breakup. Rotational disruption also appeared implausible. Pre-perihelion light curves showed no evidence of rapid rotation. The object's stable brightness suggested either slow spin or an orientation that minimized rotational variations. Without rapid rotation, centrifugal forces couldn't contribute to structural failure. That left thermal disruption as the most probable cause. But here too, the details didn't quite fit standard models. Thermal stress typically breaks objects at perihelion when the temperature gradient between sunward and shadow sides reaches maximum. The delayed timing of 3I Atlas's fragmentation, 24 minutes after closest approach, suggested a slower process, perhaps thermal creep or phase change in materials that required time to propagate through the structure. Thermodynamic simulations at JPL attempted to reconstruct the internal temperature evolution. Models assumed a small, roughly spherical body with typical thermal properties for carbonaceous material. Solar heating would penetrate several centimeters into the surface, creating a temperature gradient between the hot exterior and cooler interior. As the object passed perihelion, this gradient would induce thermal stress, expansion on the surface, resistance from the cooler interior, generating mechanical strain. But the simulations revealed a problem. The predicted thermal stress, while substantial, remained below the failure threshold for most known materials. Pure ice would have sublimated long before perihelion. Rock would easily withstand the temperature gradient. Even weak conglomerates, loosely bound aggregates held together by ice or van der Waals forces, should have survived unless pre-existing fractures or unusual weakness zones existed. The researchers introduced additional complexity into the models. Perhaps the object contained pockets of supervolatile materials, substances like carbon monoxide or nitrogen ice, that remain solid at typical cometary temperatures but vaporize at temperatures well below water's sublimation point. These materials, trapped within a carbon-rich matrix, might have mobilized as temperature rose, building pressure in sealed compartments, eventually rupturing the structure from within. Yet this scenario struggled to explain the lack of gas in the fragmentation spectrum. Super-volatile outbursts should produce detectable emissions. The dry signature suggested mechanical failure without significant gas production, a body coming apart through loss of structural cohesion rather than explosive outgassing. Another theoretical avenue explored the role of interstellar processing. During its journey across light years of space, 3I Atlas would have been bombarded by cosmic rays and exposed to ultraviolet light from distant stars. This radiation gradually alters surface chemistry, creating complex organic compounds, cross-linking carbon chains, building a processed mantle distinct from the pristine interior. Perhaps this altered layer provided cohesion during the cold of space, but failed when heated, its binding chemistry disrupted by solar radiation in ways not seen in local solar system materials. Comparison with ʻOumuamua became inevitable. That first confirmed interstellar visitor, discovered in October 2017, had exhibited its own anomalies. Most famously, precise astrometric tracking revealed a small, non-gravitational acceleration, a tiny push away from the Sun beyond what gravity alone predicted. The leading explanation invoked cometary outgassing, even though no visible coma appeared. The hypothesis suggested ʻOumuamua released just enough gas to produce acceleration without generating an observable coma, perhaps through localized vents or unusually clean sublimation. But alternative explanations persisted. Some researchers argued ʻOumuamua might be composed of hydrogen ice, a substance so volatile it would completely sublimate without leaving dusty residue. Others proposed solid nitrogen ice, like the surface of Pluto, which sublimates cleanly in solar heating. More speculative theories invoked artificial origin, a light sail pushed by radiation pressure, though this explanation found little support among mainstream astronomers. The 3I Atlas breakup added another data point to this small sample. Now 3 interstellar objects had been observed: ʻOumuamua with its mysterious acceleration and absent coma, Borisov resembling a normal comet complete with gas and dust jets, and 3I Atlas breaking apart after perihelion without significant gas emission. Each visitor challenged assumptions in different ways. The pattern suggested diversity. Interstellar space apparently contains varied populations of small bodies, icy comets like Borisov, dry carbon-rich objects like ʻOumuamua, fragile visitors like 3I Atlas. This diversity mirrors what exists in the solar system, where comets, asteroids, and transitional objects span a wide range of compositions and properties. But interstellar objects formed in different stellar environments, around stars with potentially different elemental abundances, temperature profiles, and dynamical histories. Statistical analyses attempted to constrain the population. Based on the detection rate of 3 interstellar objects over several years of sky surveys, astronomers estimated that thousands of such visitors must pass through the inner solar system annually. Most go undetected, too small, too faint, or on trajectories that don't bring them close to Earth where surveys concentrate. The detected sample represents only the brightest, closest, or most unusual members of a much larger population. This realization added urgency to understanding each detection. With so few examples available for study, every data point carries weight. The fragmentation of 3I Atlas, though destructive, provided information impossible to obtain from intact passage. The breakup exposed interior material, revealed mechanical properties, demonstrated failure modes for interstellar bodies encountering extreme solar environments. Follow-up observations continued for weeks after perihelion. The dust cloud gradually dispersed, individual particles spreading along independent orbits. Spectroscopic monitoring tracked the evolution of the debris. As dust grains cooled and moved away from the Sun, their spectra shifted, molecular bands changing with temperature and radiation environment. These measurements provided constraints on composition, grain sizes, and thermal properties. Radio telescopes searched for emissions from molecular species that might have been released during fragmentation, Hydroxyl radicals, created when solar ultraviolet breaks apart water molecules, are commonly detected around active comets. But searches for OH emission from 3I Atlas returned null results, confirming the dry nature of the breakup. Carbon monoxide and carbon dioxide, other common cometary volatiles, also remained undetected above instrument sensitivities. The European Space Agency's Solar Orbiter mission, though not optimally positioned during the fragmentation, provided additional coronal images from a different viewing angle. The stereoscopic coverage allowed three-dimensional reconstruction of the dust cloud's geometry. Analysis revealed an asymmetric distribution, with more material ejected in specific directions, possibly indicating non-uniform internal structure or rotation-induced asymmetries in the breakup process. Infrared observations from ground-based telescopes caught the cooling dust cloud in thermal emission. The infrared spectrum showed broad silicate features suggesting the presence of rocky minerals alongside carbon compounds. This mixed composition resembled certain carbonaceous chondrite meteorites found on Earth, primitive rocks rich in organic compounds and fine silicate grains. Perhaps 3I Atlas had consisted of similar material, an interstellar analogue to the building blocks that accreted into asteroids and comets in the early solar system. Theoretical modelers explored mechanical failure mechanisms for carbon-rich, volatile-poor bodies. Laboratory experiments on terrestrial analogues, carbonaceous samples subjected to thermal cycling and vacuum conditions, demonstrated that certain organic-rich materials lose cohesion when heated, undergoing phase transitions or chemical restructuring that weakens binding between grains. Perhaps 3I Atlas contained materials that behaved similarly, maintaining integrity in the cold of space but failing when solar heating altered their properties. The delayed timing of the breakup, 24 minutes after perihelion, suggested a thermal diffusion timescale. Heat takes time to penetrate into the interior, propagating inward at rates determined by thermal conductivity and heat capacity. For a 50-meter object with typical thermal properties, thermal waves would penetrate several meters in the span of minutes to hours. Perhaps the failure occurred when this thermal wave reached a critical depth, destabilizing a structural layer that had held the object together. Alternative scenarios involved phase changes in internal materials. Certain molecular compounds undergo structural transitions at specific temperatures, crystalline to amorphous transitions, or chemical decomposition events. If 3I Atlas contained materials near such a transition temperature, solar heating might have triggered a delayed cascade as the phase front propagated inward, progressively weakening the structure until catastrophic failure occurred. Archived Atlas wide-field survey images were reanalyzed with enhanced processing techniques. One frame from November 18th, captured hours before perihelion, showed a marginal detection, a slight excess brightness in one pixel that might represent localized dust emission. The statistical significance barely reached the 2 sigma threshold, making it uncertain whether the feature was real or noise. If real, it might indicate precursor activity, minor surface disruption beginning before the main event. But confirmation proved impossible. The anomaly appeared in only a single frame, too fleeting to verify. The CT Institute reviewed the observations for any anomalous signatures that might suggest artificial origin. This analysis, though speculative, followed protocol established after ʻOumuamua's unusual properties sparked brief discussions about non-natural explanations. Searches for radio emissions, optical flashes, or peculiar orbital adjustments all returned negative results. The fragmentation and all associated observations remained consistent with natural processes, a small body from interstellar space meeting its end in the Sun's gravitational well. Institutional reports circulated among the international astronomical community. The International Astronomical Union's Minor Planet Center issued formal circulars documenting the discovery, trajectory, and fragmentation. NASA's Planetary Defense Coordination Office noted the event as an example of solar system dynamics, though the object posed no threat to Earth. The European Space Agency's Near-Earth Object Coordination Center added 3I Atlas to their catalogue of unusual solar system visitors. Research papers began appearing in preprint archives. Titles captured the scientific puzzlement. Post-Perihelion Fragmentation of Interstellar Object, 3I Atlas, Implications for Composition and Structure. Comparative Analysis of Interstellar Objects, ʻOumuamua, Borisov, and 3I Atlas. Thermal models of small body fragmentation in the inner heliosphere. Each paper attempted to reconcile observations with theory, proposing mechanisms, testing hypotheses, acknowledging uncertainties. The scientific method proceeded in its deliberate way: observation, hypothesis, prediction, comparison. But gaps remained. The destruction of 3i Atlas occurred too quickly for detailed monitoring. Its small size limited the information extractable from spectroscopy. Its origin lay hidden across light-years of distance, in a stellar system unknown. Philosophical questions accompanied the technical analysis. What? Processes governed planet formation around other stars? Did interstellar visitors represent failed planets, debris from catastrophic collisions, comets ejected during system formation? How common were such objects in the galaxy? How diverse were their compositions? The data accumulated over 6 weeks of observation represented humanity's most extensive study of this particular visitor. But that data captured only surfaces, only reflected light, only what crossed millions of kilometers of space to reach waiting instruments. The interior had vanished in the fragmentation, dispersed into dust now spreading along a billion-kilometer orbital path. Comets break when they vent. Asteroids crack when they spin. This object did neither. What kind of rock survives interstellar cold, resists solar heat, then falls apart in stillness? The coronagraph continued scanning the solar corona long after 3i Atlas dispersed. Empty frames accumulated in the archive, documenting the slow fade of the dust cloud, the gradual return to baseline. By early December, no trace remained above the detection threshold. The visitor had vanished, reduced to particles too small and scattered to track individually. The orbital calculations extended into the future. Each dust grain now followed its own trajectory, perturbed by solar radiation pressure, planetary gravitational tugs, and the subtle influence of the Yarkovsky effect, a symmetric thermal emission that provides tiny acceleration over long timescales. Most particles would eventually escape the solar system, carrying fragments of 3i Atlas back into interstellar space. A few might be captured by Jupiter's gravity or collide with inner planets, but the majority would drift outward, joining the tenuous cloud of dust between stars. Analysis of residual trajectory data confirmed no large fragments survived. If the object had split into multiple kilometer-sized pieces, they should remain detectable for months, their brightness declining gradually with increasing distance. Deep searches found nothing. The fragmentation had been total, a structural failure that reduced the entire body to rubble and fine dust. This completeness suggested fundamental weakness, a compositional structure unable to withstand even modest thermal or mechanical stress. Researchers compiled the observational timeline into comprehensive datasets. 6 weeks of tracking, hundreds of images, dozens of spectra, all archived in international databases accessible to the scientific community. Future researchers studying interstellar objects would reference this material, comparing new discoveries against the established sample. Each visitor added information, constraining theoretical models, revealing the diversity of objects wandering between stars. The comparison between the 3 confirmed interstellar objects highlighted their differences. ʻOumuamua, elongated, tumbling, exhibiting mysterious acceleration without visible outgassing, surviving solar passage, intact. Comet Borisov, classical cometary behavior, abundant gas and dust production, composition similar to local comets, intact nucleus throughout observation period. 3. Atlas, carbon-rich, volatile-poor, stable until perihelion, then complete disintegration without significant gas emission. This diversity suggested that planetary systems around other stars produced varied populations of small bodies, just as the solar system contains comets, asteroids, Kuiper belt objects, and transitional populations. But the sample size remained frustratingly small. 3 objects across 4 years, insufficient to draw definitive conclusions about galactic populations. Statistical projections suggested tens of thousands of similar visitors passed through undetected, but detection required favourable geometry, sufficient brightness, and alert sky surveys. Institutional planning responded to this limitation. Proposals emerged for dedicated interstellar object surveys, telescopes designed specifically to detect and track visitors from beyond the solar system. The Vera Rubin Observatory, scheduled to begin operations in Chile, would survey the entire visible sky every few nights, its sensitivity enabling detection of objects far fainter than current capabilities. Models predicted Rubin might find several interstellar visitors per year, rapidly building a statistical sample. But even extensive surveys faced limitations. Most interstellar objects would be detected only during their brief passage through the inner solar system, allowing weeks or months of observation before they receded into darkness. Physical characterization required brightness, sufficient reflected light to enable spectroscopy, thermal measurements, detailed imaging. Small visitors like 3i Atlas pushed observational limits even at closest approach. Some researchers advocated for interceptor missions, spacecraft capable of rapid deployment to rendezvous with newly discovered interstellar objects. The technology for such missions remained under development. Chemical rockets lacked the speed for timely interception. Nuclear propulsion or solar sails might enable faster response, but both technologies required substantial development, and the unpredictability of interstellar object trajectories complicated mission planning. By the time an object was discovered and characterized, optimal launch windows often had passed. The fragmentation of 3i Atlas illustrated another challenge. Visitors might not survive solar passage intact. If an object disintegrated before detailed characterization, the opportunity for close study vanished. This motivated proposals for observation campaigns beginning at maximum possible distance, before perihelion, maximizing data collection before potential destruction. Theoretical work continued exploring composition and structure models. The carbon-rich, volatile-poor profile suggested formation in regions depleted of water ice, perhaps the inner regions of another star's protoplanetary disk, or in molecular clouds with unusual chemistry. Carbon monoxide ice, abundant in cold molecular clouds, might provide cohesion in interstellar conditions but sublime rapidly when heated, though this scenario struggled to explain the lack of CO emission during fragmentation. Alternative theories invoked organic polymers, complex carbon chains formed by radiation processing in space. Laboratory experiments demonstrated that simple ices exposed to ultraviolet light and cosmic rays gradually form refractory organic materials, tar-like substances resistant to further sublimation. Perhaps interstellar processing had converted 3i Atlas's surface into such materials, creating a cohesive but brittle matrix that failed under thermal stress. The mechanical failure mode remained uncertain. Did the object fragment from outside in, surface layers spalling off as internal materials expanded? Or inside out, internal pressure building until the structure ruptured? The observational evidence, delayed fragmentation, low ejection velocities, dry dust, favoured gentle mechanical disintegration over explosive disruption, but the exact mechanism remained elusive. Archival searches examined historical records for possible previous detections. Occasionally, survey images capture transients that are recognized only in retrospect. Faint streaks dismissed as artifacts, but later revealed as real objects. Automated searches of digitized plate archives from decades past found no credible precursors. If 3i Atlas had visited before, it left no trace in historical records. This raised questions about interstellar object return rates. Orbital calculations showed 3i Atlas arrived on a hyperbolic trajectory that would carry it back into interstellar space, never to return. Its first passage through the solar system was also its last. Most interstellar visitors likely followed similar one-time trajectories, chance encounters determined by galactic dynamics, with no possibility of repeat observation. Gravitational focusing by the Sun did provide some advantage. Any object passing near the solar system would be deflected by solar gravity, preferentially steering visitors toward the inner regions where planets orbit and telescopes scan. This focusing effect increased detection probability, making the Sun's gravity well act as a natural attractor for interstellar objects. Still, the vastness of space meant most visitors passed too far away for detection, their distant traverses remaining forever unknown. The philosophical implications stirred quiet discussion. Humanity had observed the destruction of a visitor from another stellar system, a witness to material that formed light years away, in conditions perhaps unlike anything local. The chemistry of 3i Atlas had been shaped by a different star's radiation, different abundances of elements, different temperatures and pressures in the planet-forming disk. That chemistry proved inadequate for surviving solar passage, but for 4 years or more it had endured the cold and radiation of interstellar space. What forces drove such objects into interstellar trajectories? Gravitational scattering during planet formation was the leading explanation. Young planetary systems are chaotic. Planets migrating, asteroids colliding, comets swinging through on eccentric orbits. Close encounters with forming gas giants could accelerate small bodies to escape velocity, launching them into the galaxy. Simulations suggested every planetary system ejected more mass than it retained, populating the galaxy with debris from planet formation epochs. This mechanism implied a vast population. Every star that formed planets likely launched billions of comets and asteroids into interstellar space. Across the galaxy's hundreds of billions of stars, the total number of interstellar objects could reach unfathomable values, a diffuse sea of wandering rocks and ice, drifting for millions of years between rare stellar encounters. Detection would always remain a sampling problem. Of the countless objects drifting through interstellar space, only those passing very close to the Sun, within a few astronomical units, stood any chance of discovery, and of those, only the larger, brighter objects registered on current surveys. The smallest visitors, perhaps the most numerous, remained invisible. The data from 3i Atlas joined a growing archive of small body observations, comets, asteroids, meteoroids, and now interstellar visitors. Each observation contributed to understanding planetary system formation and evolution. Each object carried information about conditions in its birth environment. The challenge lay in extracting that information from limited observations, inferring internal properties from surface measurements, reconstructing histories from fragmentary evidence. Dust from the fragmentation would drift for years, gradually dispersing along the orbital path. Some particles might eventually collide with Earth's atmosphere, vaporizing as meteors, their interstellar origin impossible to determine from a brief flash of light. Others would escape the solar system entirely, returning to the space between stars, carrying their processed chemistry back into the galactic environment. The astronomical community documented lessons learned. Future detection protocols would prioritize immediate follow-up of interstellar candidates, maximizing observation time before perihelion. Spectroscopic surveys would begin at earliest detection, capturing composition data before potential fragmentation. Coordination between ground and space-based observatories would improve, ensuring multiple independent datasets for critical events. But planning could not overcome fundamental limitations. Small interstellar objects would remain difficult to characterize. Their faintness limited spectroscopic quality. Their speed through the inner solar system compressed observation windows. They're unpredictable. Trajectories prevented advanced planning. Each detection would be a race against geometry and brightness, scientists scrambling to extract maximum information before the visitor receded beyond reach. The pattern across ʻOumuamua, Borisov, and 3i Atlas revealed something about observational bias. Each object challenged expectations in different ways. ʻOumuamua with its acceleration, Borisov with its unremarkable normalcy, 3i Atlas with its fragmentation. Perhaps the unusual properties were what enabled detection in the first place. Objects behaving exactly as expected might pass unnoticed, their motion and appearance indistinguishable from local solar system bodies. Only anomalies triggered attention, warranted follow-up, secured observing time on major facilities. This bias complicated population statistics. If unusual objects were preferentially detected, the observed sample might not represent typical interstellar material. The true population could consist primarily of unremarkable objects that blended into background noise, noticed by surveys but never recognized as extraordinary. Only future detections, building larger statistical samples, could reveal whether the current sample was representative or skewed toward outliers. Research groups proposed classification schemes for interstellar objects, attempting to organize the diversity into meaningful categories. One system distinguished between active objects showing cometary behavior and inactive bodies lacking gas emission. Another focused on composition, icy, rocky, or carbonaceous. A third emphasized dynamics, hyperbolic velocity, perihelion distance, orbital inclination. Each scheme provided different insights, highlighting different aspects of the population. But with only 3 confirmed examples, classification remained premature. The sample size was too small to establish meaningful categories. Each new detection might reveal properties that defied existing schemes, requiring revision or expansion. The field remained in its exploratory phase, accumulating observations, testing hypotheses, building theoretical frameworks that would eventually mature into comprehensive understanding. Graduate students began thesis projects analysing interstellar object data. Papers examined fragmentation mechanisms, compositional diversity, detection biases, population statistics. Conferences featured dedicated sessions on interstellar visitors, researchers presenting latest findings, debating interpretations, planning future observations. The field was young, energetic, driven by curiosity about material from beyond the solar neighbourhood. Public interest fluctuated. ʻOumuamua had captured widespread attention, its unusual properties sparking speculation and media coverage. Borisov received less fanfare. Its cometary behaviour, while scientifically valuable, lacked the mystery that engaged general audiences. 3i Atlas attracted moderate interest, the fragmentation event providing dramatic visuals, and an unexplained mystery that resonated with public curiosity about space phenomena. Educational materials incorporated interstellar objects into curricula. Astronomy textbooks updated chapters on small solar system bodies to include sections on interstellar visitors. Planetarium shows featured animations of ʻOumuamua's tumbling passage and Borisov's cometary tail. Online videos explained the science behind detection and characterization, reaching audiences far beyond academic circles. The search for interstellar objects became a recognized subdiscipline within planetary astronomy. Researchers specialized in rapid follow-up observations, developing techniques for extracting maximum information from brief detection windows. Software tools automated candidate identification, filtering survey data for objects with hyperbolic trajectories. International networks coordinated observations across time zones, ensuring continuous coverage during critical periods. Some scientists advocated for missions beyond detection and observation. Sample return missions could retrieve material from interstellar objects, bringing pristine fragments back to Earth for laboratory analysis. Such missions faced enormous technical challenges. The high velocities and unpredictable trajectories made rendezvous extraordinarily difficult, but the scientific payoff would be immense. Direct analysis of interstellar material would reveal isotopic ratios, mineral structures, organic chemistry, and other properties impossible to measure remotely. Near-term proposals focused on more modest goals. Flyby missions might pass close enough to capture high-resolution images and mass spectrometry data without requiring full rendezvous. These missions could be kept on standby, ready for rapid launch when a suitable target appeared. The economic and political challenges of maintaining standby spacecraft were substantial, but technical feasibility studies suggested such missions lay within current capabilities. The night sky continued its eternal motion, stars wheeling overhead, planets tracing their ancient paths. Somewhere among those stars, the system that had birthed 3i Atlas pursued its own evolution. Planets orbiting, perhaps life emerging, perhaps civilizations gazing at their own night sky and wondering about worlds beyond their reach. The material that had formed 3 Atlas came from that distant system's planet formation process, ejected eons ago, wandering through the galaxy until chance brought it near the Sun. The fragmentation had scattered that material, but it did not return it to its origin. The dust particles now followed solar orbits, some eventually escaping into interstellar space but on different trajectories than their arrival path. In a sense, 3i Atlas had been captured by the Sun, its material incorporated into the solar system's inventory of small bodies, joining the comets and asteroids and dust that already populated the space between planets. Deep time scales made such events inevitable. Over millions of years, countless interstellar objects passed through the solar system. Some were captured, their orbits altered by planetary encounters until they became permanent residents. Others passed through unchanged, their hyperbolic trajectories carrying them back into the galaxy. The exchange worked both ways. The solar system likely lost as much material to interstellar space as it gained from passing visitors. This interstellar traffic connected stellar systems across the galaxy. Material from one system mixed with debris from another, gradually homogenizing the chemistry of the interstellar medium. The organic compounds detected on 3i Atlas, complex carbon chains formed in another stellar environment, would now disperse through the solar system, potentially reaching planets, perhaps contributing their chemistry to whatever processes occurred on those worlds. astrobiological implications remain speculative but intriguing. If life existed in the system that produced 3I Atlas, could biological material survive ejection and interstellar transit? Laboratory experiments showed that certain microorganisms could endure vacuum, radiation, and extreme temperatures when protected within rock matrices. Panspermia theories propose that life might spread between stellar systems via such natural mechanisms, though evidence remained circumstantial. The observation archive grew steadily as surveys continued. Each night, automated telescopes scanned the sky, software algorithms sifting through millions of detections, searching for the rare signatures of unusual motion. Most nights yielded routine results: known asteroids, catalogued comets, familiar objects following predicted paths. But occasionally, an anomaly appeared, a moving point of light that matched no known orbit. Each such detection triggered a cascade of follow-up. Confirmatory observations verified the object's reality. Astrometric measurements refined its trajectory. Spectroscopy probed its composition. Photometry tracked brightness variations. The coordinated effort of the astronomical community focused on extracting every possible piece of information before the visitor receded beyond detection limits. This process had played out for 3 Atlas. From initial detection in October to final observations in December, dozens of telescopes had contributed data, hundreds of researchers had analysed results, thousands of hours of observation time had been allocated. The scientific return justified the effort. A unique dataset documenting an interstellar object's fragmentation, revealing properties of material formed in another stellar system. But questions remained. The fragmentation mechanism stayed uncertain. The exact composition eluded complete characterization. The origin system remained unknown, somewhere among billions of stars, impossible to identify from trajectory alone. These unknowns motivated continued study, refinement of models, design of better instruments for future observations. The progression from ʻOumuamua to Borisov to 3I Atlas showed accelerating capability. Each detection had been characterized more thoroughly than the last, instruments and techniques improving, coordination more efficient. Future detections would benefit from this accumulated experience, enabling even more comprehensive studies. The field was learning, developing expertise, building the infrastructure needed to maximize scientific return from rare opportunities. Graduate students who cut their teeth on 3I Atlas data would become the next generation's experts. Their experience analyzing fragmentations, modeling thermal stress, interpreting unusual spectra would prepare them for future discoveries. The institutional knowledge, the subtle craft of distinguishing signal from noise, recognizing artifacts, weighing uncertainties, would be passed forward, improving the community's collective ability to extract truth from limited observations. Archives would preserve the data indefinitely. Future researchers, equipped with better models and more comprehensive datasets from subsequent detections, might return to 3I Atlas observations and extract new insights impossible with current understanding. This prospect motivated careful curation, ensuring data formats remained accessible, maintaining documentation, preserving both raw observations and processed results. The slow accumulation of knowledge characterized the scientific endeavor. Each observation added a small piece to the larger puzzle. Each theoretical insight refined understanding slightly. Over years and decades, the fragmentary pieces would coalesce into comprehensive understanding: how planetary systems form, what materials they produce, how those materials disperse through the galaxy, what becomes of visitors that enter foreign stellar systems. 3I Atlas had been one such visitor. Its journey across light years ended in the Sun's gravitational embrace, its structure failing under conditions foreign to its formation environment. The dust it became would drift for years, a diffuse memorial to a wanderer that came from elsewhere and found, briefly, scientific immortality in humanity's observational record. The telescopes continued their watch. The sky held countless more visitors, most passing undetected, a few bright enough or close enough to register on sensitive instruments. Each detection offered another glimpse into the population of objects wandering between stars, another data point constraining models, another story of material shaped by alien suns and scattered by chance into humanity's neighborhood. Observers at Mauna Loa and Haleakala maintained their vigil. The Atlas telescopes swept the darkness, automated systems processing streams of data, algorithms searching for anomalies. Most nights passed without remarkable detections, but the possibility persisted. Any night might reveal another visitor, another chance to study material from beyond the solar neighborhood, another opportunity to expand understanding of the galaxy's hidden populations. The arc of discovery stretched into the future. Next year might bring another detection. The year after, perhaps 2 more. Gradually the sample would grow, patterns would emerge, statistical significance would strengthen. The rare would become less rare. The unknown would yield incrementally to understanding. But some mysteries might persist. The origin systems of detected objects would likely remain unidentified. Too many candidate stars, insufficient trajectory precision. The full diversity of interstellar populations might take centuries to map completely. And individual objects like 3I Atlas, destroyed during observation, would retain their secrets. Interior structures never imaged, detailed compositions never measured, exact failure mechanisms never fully resolved. This incompleteness was inherent to the endeavour. Astronomy observed from afar, reconstructing reality from photons that crossed vast distances. Direct interaction remained impossible, limiting knowledge to what light and gravity could reveal. Within these constraints, the scientific community pursued understanding with creativity and rigour, designing observations to answer specific questions, developing models that made testable predictions, gradually narrowing the space of possible explanations. The dust of 3I Atlas scattered along its orbital path would fade below detection within months, but the data would persist. Archived images, calibrated spectra, orbital solutions, theoretical papers. This information would outlive the object itself, becoming part of humanity's permanent record of observations, available to future scientists equipped with better understanding and more comprehensive theories. The story of 3I Atlas joined others in the growing catalogue of cosmic encounters. Each tale revealed something about the universe, its scale, its diversity, its indifference to human observation. Objects travelled for millions of years in darkness, indifferent to whether anyone witnessed their journeys. That humanity happened to detect this particular visitor during its brief solar passage was accident of timing and technology. Yet that accident produced knowledge. From faint photons captured by silicon sensors, scientists reconstructed a visitor's final hours, its approach, its fragmentation, its dispersal. Mathematics revealed the forces at play. Spectroscopy decoded composition. Models explored possible mechanisms. The scientific method transformed raw data into understanding partial and uncertain, but grounded in evidence. The record would endure. Generations hence, researchers studying interstellar objects would reference 3I Atlas alongside ʻOumuamua and Borisov and whatever visitors followed. The early detections, crude by future standards, would mark the beginning of a field, the first systematic study of material wandering between stars, the first attempts to characterize objects formed in alien stellar environments. In this sense, 3I Atlas achieved a curious immortality. Though its physical form scattered into dust, its passage through humanity's instruments granted it lasting documentation. The visitor that broke near the sun would be remembered not for surviving but for what its destruction revealed, about material properties, fragmentation physics, the diversity of objects between stars. Are we measuring alien material, or our own limits of understanding? The question echoed through the data, unanswered. The observations documented what occurred. Fragmentation after perihelion, dust dispersal, dry composition. But the why remained elusive. Models approached explanation but couldn't fully close the gap between theory and observation. The material properties that governed 3I Atlas's cohesion and failure came from conditions humanity had never directly sampled. Another star's planet-forming region, chemical processes under different elemental abundances, structures shaped by different thermal histories. The limit of understanding was also a horizon of possibility. Each mystery identified pointed toward future discovery. The unexplained fragmentation motivated better thermal models, more sophisticated material science, deeper investigation of how carbon-rich bodies behave under stress. These investigations would proceed over years, building gradually toward comprehensive theory. Meanwhile, the ski waited. Somewhere in the darkness between stars, other visitors were already en route, their trajectories slowly converging toward the solar system. Some would be detected, adding to the catalogue. Others would pass unnoticed, their visits remaining forever unrecorded. The universe continued its ancient motion, indifferent to human curiosity, but offering endless opportunity for those patient enough to watch and wonder. The dust drifted outward, carried by solar wind and radiation pressure. Particles that had been a single object, a visitor from interstellar space, now followed independent paths. Some would escape the sun's gravity entirely, returning to the space between stars. Others would orbit for millennia before collision or ejection determined their final fates. In their dispersal, they mirrored the countless other particles populating interplanetary space, a vast cloud of debris, remnants of collisions and fragmentations, slowly evolving under gravitational and radiative forces. Among that debris, the material from 3I Atlas would be indistinguishable. No marker identified its interstellar origin. Its chemistry might differ slightly from local materials, isotopic ratios reflecting formation around another star. But without capture and laboratory analysis, these subtle signatures would remain undetected. The visitor had passed, contributed its atoms to the solar system's inventory, and vanished into the background. The investigation concluded not with answers but with refined questions. What range of material properties existed among interstellar objects? How did formation environments around different stars affect small body composition? What mechanical structures could survive interstellar transit but fail under solar heating? These questions would guide future research, shaping observation strategies, motivating theoretical work, defining the next generation of studies. Silence returned to the corona. The instruments continued recording, but the event had passed. The data resided in archives, awaiting analysis, reanalysis, comparison with future detections. The scientific community moved on to other projects, other observations, other mysteries. But 3I Atlas remained in the literature, a case study in fragmentation, a data point in population statistics, a reminder of the visitors that pass through darkness between stars. The telescopes watched. The algorithms searched. The universe offered its secrets reluctantly, revealing only what persistent observation could extract. And humanity watched back, driven by curiosity about the cosmos and its place within, accumulating knowledge piece by piece, patient in the face of vast distances and deep time. In the end, 3I Atlas was both ending and beginning, the destruction of a visitor from distant reaches, and the opening of new questions about the galaxy's wandering population. What arrived from elsewhere had departed, but the information it provided would ripple forward, shaping understanding for years to come. The light from distant stars continued its journey, photons crossing space, some eventually captured by telescopes, translated into data, transformed into knowledge. Among those stars, perhaps the one that birthed 3I Atlas still burned, its planets still orbiting, its comets still wandering outward to be scattered by gravity into the greater galaxy. The cycle continued: formation, ejection, transit, detection, connecting stellar systems across light years through the currency of wandering matter, and humanity observed, recorded, analysed, and wondered. The visitor broke in silence. The data remained. The questions persisted. The search continued, eyes turned toward darkness, waiting for the next anomaly, the next visitor, the next glimpse of what lies beyond the solar neighbourhood in the vast spaces between stars.